Today, we're going to dive into one of the absolute coolest, most powerful ideas in all of physics. It's called scattering theory. And honestly, it's how we figured out the universe's deepest, darkest secrets, from what an atom is actually made of to the invisible forces holding it all together. And the craziest part? We've done it all without ever seeing any of it.
I mean, really, just stop and think about that for a second. When you get down to the subatomic level, things like neutrons or the quarks inside them, you can't just pop them under a microscope. They're fundamentally impossibly small. So how in the world do you figure out what they're like? What's their shape? What are the rules they play by?
The answer? Well, it's so simple, it's almost funny. You throw things at it. Yep, that's it. The whole mind-blowing field of particle physics pretty much boils down to this. You take a particle you understand, you fire it at the mystery object, and then you watch very, very carefully to see how it bounces off.
To really get a feel for this, let's forget about quantum physics for a minute and start with a simple analogy, something that really gets to the core of the idea.
Okay, so I want you to picture this. You're standing in a room that is completely, totally dark. Somewhere in the middle of that room is an object, but you have no idea what it is. You can't see it, you can't walk over and touch it, but you do have a giant bucket of marbles. So what's the plan?
Well, you start throwing those marbles, right? You just start chucking them into the darkness. And by listening to where they hit the floor and mapping out their paths in your head, you can actually start to build a picture. If a ton of marbles bounce right back at you, hey, you probably hit a flat surface. If they scatter out in this wide, gentle arc, maybe you're dealing with a sphere. The pattern of those scattered marbles, that's what reveals the shape of the hidden object.
Okay, so that's the basic concept. Marbles in a dark room. Now let's see how that simple idea gets supercharged into a real, high-tech, universe-exploring physics experiment. So in a real lab, your bucket of marbles gets replaced by something a bit more sophisticated, a perfectly controlled beam of particles, maybe electrons, shot out of a giant particle accelerator. And your invisible object in the middle of the room, that becomes our subatomic target, something like a single neutron. And the actual process is amazingly similar to our little marble game, just with way, way more precision. Scientists get their beam of particles ready, they aim it smack at the target, and then they have these incredibly sensitive detectors all around it, measuring exactly where every single particle goes after the collision. What they get is a super detailed map of the scatter pattern. Now, that scatter plot, it's not just a pretty picture. It's a precise measurement of something with a fancy name, the differential cross-section. But don't let the name scare you. You can just think of it as the effective size of the target from different angles. It's the answer to the question, okay, how likely is a particle to get knocked off into this specific direction compared to that one? This is the pattern. This is the effect we can actually see and measure. But here's the thing. The pattern is just the clue. What we're really after is the why. What fundamental force caused that specific pattern? All of that hidden information is locked inside something called the scattering amplitude. The amplitude is like the deep-down blueprint of the interaction. It's this core number that when you square it, tells you the probability that a particle will fly off in a certain direction. The pattern is what we observe. The amplitude is the secret we're trying to steal. And this right here, this is the golden ticket. This is the key that connects everything. The differential cross-section, that's the pattern we can actually measure in the lab, is mathematically equal to the absolute square of the scattering amplitude, which holds all the juicy physics about the forces involved. So by meticulously measuring the pattern on the left, we can work our way backward and figure out the hidden fundamental properties of the interaction on the right. It's brilliant.
But you knew there was a but coming, didn't you? This is quantum mechanics after all, so things have to get a little bit weird. Our marbles, they aren't exactly the solid little balls we've been picturing.
Because down at the quantum level, every particle also has a wavy side to its personality. It behaves like a wave. So how does that completely change the game? Well, instead of a single marble hitting a target, I want you to imagine an incoming wave of energy washing over it. This interaction then creates a new wave, a spherical one that spreads out from the target in all directions. And here's the cool part. Just like ripples in a pond, that new scattered wave interferes with the original incoming wave. This creates this incredibly complex, beautiful pattern of peaks and valleys that contains so much more information than a few bouncing marbles ever could. So, okay, we've got this super intricate interference pattern, but how do physicists actually read it? How do you look at that mess of waves and translate it back into a clear, simple understanding of the forces that made it?
Well, physicists have some really clever mathematical tools, and one of the most powerful is called the Born approximation. Think of it like a shortcut. It works amazingly well when the force doing the scattering is relatively weak, and in that case, the relationship between the pattern and the force becomes stunningly simple. The pattern, for all intents and purposes, becomes a direct map of the forces involved. You can literally just read the nature of the force right out of the data. It's an incredible trick.
And the payoff for all this mind-bending theory and these massive experiments? Well, it's been nothing short of immense. This whole technique of throwing quantum waves at invisible things has totally transformed how we see the universe.
Let's just take the neutron. For the longest time, everyone figured it was just a fundamental neutral little ball. But then, physicists started scattering high-energy electrons off of it, and the pattern they saw, it was wild. It could only have been made if the electron was hitting tiny, charged, point-like things inside the supposedly neutral neutron. Bam! That was the first solid evidence for quarks. And it got even weirder. These experiments showed that the force holding quarks together actually gets weaker the closer they get. That was a huge piece of the puzzle that led to the theory of the strong nuclear force, quantum chromodynamics.
It all comes down to what the physicist R. Shankar said. Scattering isn't just one way to learn about the subatomic world, it is truly one of the best ways. It's our #1 tool for exploring the fundamental nature of reality. So, from seeing inside the atom to discovering the bizarre inner lives of quarks, scattering theory has been our flashlight in the dark. As we build more powerful accelerators and more sensitive detectors, you have to wonder, what new, invisible layers of reality are we going to uncover next? What huge questions about things like dark matter or even gravity itself are we finally going to answer? All by just throwing things at them.